You know that feeling when you're trying to explain a complex idea and it just doesn't quite click for someone? Or maybe you're the one trying to grasp it and it just isn't quite clicking for you. Today we're taking a deep dive into something incredibly fundamental, something we all encounter literally every single day, but rarely think about on a deeper level.
Yeah.
Matter. Seriously, how do humans, especially children, actually come to understand what stuff is made of?
It's a really fascinating question because what seems, intuitive to us now about atoms and molecules, well, it's actually a complex conceptual journey.
Right.
Our mission in this deep dive is to give you a shortcut, basically, through a stack of fascinating research papers and studies. These sources focus on how students' understanding of matter from everyday objects to the invisible world of particles develops. And importantly, all the surprising challenges they face along the way.
Exactly. So get ready. We're going to unpack the surprising journey of conceptualizing matter, from elementary school all the way up to advanced chemistry. We'll explore what it means for how we learn, how we teach, and maybe even how you understand the very fabric of the world around you. Well, okay, so let's unpack this. Our journey starts with the very young learners, typically grades 1 to 3. For them, understanding matter is really all about what they can perceive.
It's direct experience.
Yeah, it's simply water, iron, wood. Their ideas are shaped by simple characteristics, what things look like, how they use them, or even just what familiar substances they remind them of.
You see this really vividly when younger students observe a chemical reaction like baking soda mixing with vinegar. They'll describe it as fizzing or bubbling. Okay, fair enough. Or sometimes just like mixing baking soda with water.
So just comparing it to something familiar.
Exactly. And what's surprising is they might even think the vinegar actually turns into another substance. Just because its color changes or its smell lessens when it's mixed, their understanding is just so anchored in those immediate sensory perceptions, not on any kind of deeper transformation.
That makes so much sense. And, it gets even more interesting around grades 5, 6. There's this curious belief that if you put baking soda in water, it can't just disappear, even if you can't see it anymore.
Right. The logic they use is quite revealing.
It really is. The reasons they give are things like, because I saw it put in, or it's a solid and couldn't evaporate, or even it stays in what you dissolve it in. It just shows how those initial concrete perceptions really anchor their understanding. Makes it incredibly hard to let go, even when something seems to vanish.
Indeed. And these early intuitive ideas also show us some pretty significant barriers to understanding the particulate nature of matter, or PMM. That's essentially the idea that everything is made of tiny, separate, invisible bits.
Which is totally counterintuitive at first.
It absolutely is. Many children instinctively believe matter is continuous, like a solid block, not made of these discrete particles. They might think particles are always touching, with no empty spaces between them. Or, and this one is really stubborn, they might believe that the particles themselves possess the macroscopic properties of the substance.
Like what?
Well, imagine thinking an individual atom of copper is malleable, like you could bend it.
Okay, got it.
These early ideas are often incredibly resistant to change.
So if their everyday experience tells them matter is continuous and that atoms can be bent like copper, how do we guide students to look beyond what's immediately visible?
That's the core challenge, isn't it? As students progress, especially from grade 4 onwards, they start perceiving physical properties and changes that go deeper than just surface appearance. This is where the building blocks really start to come into play. They begin to construct concepts of volume and weight, and they learn that careful measurement can reveal consistent, predictable rules about how things behave. Rules that our senses alone just can't detect. This is such a critical step.
So moving beyond just looking.
Exactly. For instance, they start to grasp the simple relationship that if you double the volume of a certain material, you double its weight. That kind of basic proportionality. And this foundation prepares them for later concepts like density.
That's a huge conceptual leap. And another significant step, I imagine, is learning to differentiate weight from mass. Weight being affected by gravity, while mass is the actual amount of stuff.
Spot on. It's like your weight changes on the moon, but the amount of you, the mass, doesn't. Different types of scales can actually help highlight these distinctions, showing how weight is related to force and gravity, while mass is this more fundamental quantity of material.
Right. So this transition from just observing to actually measuring and abstracting, that's vital.
It's absolutely the groundwork for the next big leap. the invisible world of atoms and molecules. A central achievement from middle school onward is developing an understanding of the atomic molecular theory, or AMT. That's the foundational idea that all matter is composed of atoms and molecules, and recognizing its powerful ability to explain why things behave the way they do, helping them distinguish between physical and chemical changes.
Okay, here's where it gets really interesting, I think.
Hmm.
Particles appear, but it's gradual, right? Students' spontaneous descriptions of substances, they slowly evolve.
They really do. They move from talking about how something looks or what it's used for to its physical properties, and then eventually, for high school chemistry students, they finally start describing things in terms of elements, compounds, atoms, molecules, maybe even intermolecular
But it
forces.
takes a while to get there.
Oh, yeah. It's really only high schoolers, with some exceptions maybe, who consistently use terms like molecules and atoms as core explanatory ideas.
That gap is pretty clear.
To illustrate that gap, think about baking soda again. Up until grade 8, when asked about its composition, students often just admitted they didn't really know, or they'd describe it using familiar powders like sugar, salt, or flour.
Wow. Just falling back on analogies.
Exactly. It highlights how far they are from a particle-based understanding until that theory is explicitly introduced and, crucially, grasped. And this whole undertaking, understanding AMT, it's demanding. It requires imagining things far removed from their everyday experience, and it challenges these deeply entrenched assumptions like matter being continuous or infinitely varied.
So they have to accept it based on what? Indirect evidence.
Precisely. Things like the compressibility of gases. You can't see gas particles, right? But you can see a gas compress, which is best explained by imagining tiny particles with empty space between them. It's inference, not direct sight.
So we have the visible world, the measurable world, and then there's a visible world of particles. But chemistry adds another layer of complexity, this triplet relationship people talk about. Phenomena can be understood at three levels: macroscopic, submicroscopic, and symbolic.
That's right. The macroscopic is what we observe directly, say, a gas diffusing across a room. We see the effect. The submicroscopic is the unobservable world of molecules, ions, electrons, what's actually happening down there.
The explanation level.
Kinda. And what's fascinating here is that even the term particle itself can be confusing. Young students might think that visible grains of salt are the particles their teachers are talking about, rather than the vastly smaller hypothetical entities we actually mean in chemistry.
That's a really important distinction. And then there's third level, symbolic. The chemical equations, H-zeros, formulas, diagrams, basically chemistry shorthand language.
Yes, and while this symbolic language is an incredibly powerful tool for experts, for novices, well, it can actually impede understanding. It adds considerable extra demands when students are already struggling with these abstract concepts.
So it's like learning a new language on top of a completely new way of thinking about the world.
Pretty much. A perfect example is chemical equations. Students might learn to write an equation with the correct formulas, maybe even in higher grades, but then they forget to add the coefficients to balance it.
Ah, the balancing act.
Right. And forgetting that suggests they don't fully grasp what a balanced chemical equation actually means. In terms of particle counts, the conservation of matter during a reaction. And moreover, diagrams representing the submicroscopic level can be misinterpreted too. If students don't understand the conventions of the representation, or if they don't make those crucial links between what they see at the macro level and what's supposedly happening at the submicro level,
They just see dots on a page.
essentially, they might see dots but not connect them meaningfully to actual atoms interacting.
Okay, so once we start visualizing matter, the next big challenge, and maybe one of chemistry's most notorious, is understanding how it changes. Chemical reactions.
Huge hurdle.
Many students, especially younger ones, they don't really view chemical reactions as a complete transformation of the matter itself. Is that right?
That's often the case. Instead, they might see it more as just a change in appearance or physical state, or even just a simple mixing, where the products are somehow just a blend of the initial substances still hanging around.
Like seeing two paints mixed to make a new color, but thinking the original paints are still there, just jumbled up.
That's a good analogy. They don't grasp the idea of substances fundamentally rearranging into new substances. And this raises an important question. Why do students think this way? What's the reasoning?
Yeah, what's behind it?
Often, their explanations for chemical processes are kind of anthropomorphic. They attribute human-like needs or wants to atoms.
Oh, like atoms want to have full shells.
Exactly. Atoms need or want to obtain full electron shells. This full shells explanatory principle is incredibly common, and it can actually hinder a deeper understanding of other bonding types later on, like metallic or ionic bonding, which aren't quite so simple.
So it's a helpful starting point maybe, but limiting.
Potentially, yes. Researchers also call this teleological thinking, the idea that things act towards a goal or purpose. Think of saying a ball wants to roll downhill. That's applying purpose to physics. And surprisingly, these kinds of teleological assumptions about chemical stability can persist even with advanced training.
Interesting. You also see a common challenge with the concept of randomness, right? Especially with gas particles.
Oh, definitely. Many students incorrectly believe that in, say, a small container of air, the lighter hydrogen particles float to the top and the heavier oxygen particles sink to the bottom, just due to weight.
Like oil and water, but with gases.
Kind of, yeah.
Yeah.
They often simply lack the concept of random, constant motion in collisions that keeps everything mixed up.
It's that deep-seated intuition again. Heavy things sink, light things float.
Exactly. Applied at a scale where random thermal motion completely overrides those tiny weight differences in a small volume. And this brings us nicely to the crucial role of models, curriculum, and instruction in guiding students' understanding.
Because we need tools to bridge these gaps.
Precisely. Scientists use models constantly, it's how they think, but students often lack experience in actually developing, using, revising, and evaluating their own ability to model abstract concepts, especially something like the particulate nature of matter. They tend to see models as just fixed pictures, not as tools for thinking and predicting.
Which is why visualizing the unseen is so critical. Multimedia tools, like dynamic animations and simulations, seem absolutely vital here.
They really are. They can effectively present the dynamic and interactive nature of chemical phenomena. They allow students to explore, to manipulate different parameters, temperature, pressure, and even ask those what-if questions.
See what happens if you heat things up, for example.
Exactly. The impact of these tools can be significant. Dynamic animations, in particular, can really facilitate students' understanding of the randomness of motion, and maybe the relationship between particle size and average speed. Even simple things like role-play activities where students physically act as particles have been shown to help them grasp the randomness and interaction involved in processes like diffusion.
Getting them to embody the concept.
Yeah, making it less abstract.
So how does all this inform how we actually design what and how we teach? Curriculum design sounds like it truly matters.
It's fundamental. Researchers use tools called learning progressions to map out how students' ideas typically become successively more sophisticated over time. It's important to note these progressions aren't inevitable developmental stages. They are crucially dependent on the instructional practices used.
So good teaching can guide students along these paths.
That's the idea. These progressions can help connect curriculum, instruction, and assessment in a more coherent way, guiding students through these complex ideas step by step, building on their prior understanding.
And this perspective, it shifts how we view misconceptions, doesn't it?
It really should. Instead of viewing student misconceptions as just errors to be fixed or erased, a more productive approach is to see them as valuable starting points, as resources for developing greater knowledge. They show us how the student is thinking.
Working with their current ideas rather than just against them.
Precisely. What the research really emphasizes is that building a robust, scientifically accurate understanding isn't about quick fixes. It's about consistent, deliberate practice with these more sophisticated scientific ideas and assumptions over many years. If a curriculum focuses too much on just the quantitative stuff, maybe the algorithms for solving problems, and not enough on explicit practice with these core conceptual assumptions about matter,
Then the real understanding suffers.
that's what the evidence suggests. True conceptual understanding gets left behind.
So wrapping this up, what does this all mean for you, the learner, listening to this? Our deep dive reveals that grasping this really fundamental concept of matter isn't just a single aha moment. It's a complex, gradual journey. It's about profound conceptual change.
Yeah, it involves shedding intuitive, often deeply ingrained assumptions, things that feel like common sense, and building new ones. Sometimes building ideas that go directly against what our everyday senses tell us.
And considering how persistent many of these intuitive ideas are, even among older students, maybe even adults, it raises an important question for you to think about. How many of your own intuitive beliefs about the world, perhaps about something totally unrelated to chemistry, might be subtly shaping your understanding, even after you've had formal instruction?
That's a great point. What if the way we think about the unseen in any field, economics, psychology, whatever, is always, in some part, influenced by the seen in our daily lives? And maybe more importantly, what could you gain by deliberately challenging those common sense impressions in areas you care about?